Hey, welcome. So our last video, which will be linked below, we introduced the probability generating function, or PGF for short. We kind of discussed its definition, what it is, some properties of it. But I kind of find with that sort of thing, PGFs, MGFs, CDFs, PDFs, it's a lot easier when you actually kind of get your hands on one. You can actually calculate it for a specific distribution. You can play with it, see the different results, see what you get. So today in this video, we're gonna calculate the PGF of a couple of simple distributions, see how the actual calculation works, discover some properties along the way, and we're gonna use these two properties that we talked about in the last video to make sure what we did is correct. So top example, plugging in 0. Remember, we use this pi symbol for the PGF instead of p because we use p for probability. So pi, the PGF of x evaluated at 0 must be equal to the probability that x equals 0. So that's the first property. And then the second property is the PGF of x evaluated at 1 must be equal to 1. So those two things must work. So to start, we're going to do probably the simplest distribution, I guess, other than uniform, probably even simpler than uniform. A Bernoulli distribution with probability parameter p. If you don't remember, Bernoulli is just basically a coin flip with probability p of getting a success. It's one trial, it's a single trial, so x can be 0 or 1. Probability of success, probability 1 minus p of failure. So again, we want to calculate the PGF of x, and we use this timekeeping variable s. And what helps me, well, first, before we do that, let's write out the expectation definition. Remember, it's the expected value of s to the power of x. And now it helps me whenever I see the expectation of some function of a random variable x, it helps me just to write out using Lotus, law of the unthinking statistician. It helps me to write out sort of what that expectation is and kind of work from there. So in this case, the expansion is pretty simple because the support of the random variable x is on size 2. X only takes 0 or 1. So this becomes the expected value of s to the x becomes probability that x equals 0 times s to the 0 plus probability that x equals 1 times s to the 1. And again, we're just saying, okay, the two values that x can take on, 0 or 1, and then weighted by the probabilities of those occurring, right? S to the 0 is going to be 1. Anything to the power of 0, including 0, is 1, so that goes away. S to the power of 1 is just s, so that goes away. And we are just going to be left with probability that x equals 0, that's 1 minus p, plus probability that x equals 1, that's p times s. So 1 minus p plus p times s. Pretty cool. That's a pretty simple looking formula, but that's the function for, that's the probability generating function for Bernoulli p for x. And as promised, we can kind of make sure that these satisfy our two properties. So first, let's plug in the value 0 for x. We plug in the value 0 for, plug in the value 0 for s. We plug in the value 0 for s, we're going to get 0 times p is 0. We just get 1 minus p, which indeed equals the probability that x equals 0, right? The probability that x equals 0 is just 1 minus p, so this checks out. Hooray. And then if we plug in 1, we're going to get 1 minus p plus p times 1. 1 minus p plus p equals 1. Boom. Awesome. So properties check out, so it's good news. It looks like, it's possible that the properties work and we got the wrong PGF, but in this case, we got the right PGF. We see that the properties kind of hold. Awesome. That's a very simple example. You might be thinking, let's look at a little bit more complicated example. And we're actually going to look at kind of a multi-dimensional version, or an extra-dimensional version of the Bernoulli. So we're going to look at a binomial random variable. And again, if Bernoulli is one trial with probability p of success, binomial is n trials with probability p of success on each trial, independent trials, but identically distributed. So basically think you're tossing the coin with probability p of heads, doing it n times, and you're counting the number of successes. So basically the sum of Bernoulli's. So we want to find the PGF of this, and I'm going to pause here. Instead of doing the same kind of Lotus expansion we did, we're going to try to go a different way. Okay, we're going to say, let's consider two random variables, z and y, and let's say the sum of those random variables is going to equal a third random variable, w, we're going to say that z is independent of y. That's the sign I use for independent, those two lines in the bottom line. The z and y are independent, and the sum of z and y are equal to w. Okay. Let's think about finding the PGF of w. Okay, so the PGF of w is the expected value of s to the w, right? W, again, is the sum of two other independent random variables. We can expand that. We can just plug in z and y for w, s, y plus z, right? I'm just plugging in w equals y plus z, so that's fine, or z plus y. By the rules of exponents, I can just switch this around a bit. Sy, sc. Instead of having s to the y plus z, we can have sy and sc. And because y and z are independent, we do this. We can just kind of factor those two guys out. Pretty cool. Now this step, you might be like, whoa, that's not okay. We can't do that. So we're gonna take a second and kind of prove that this is true. It is true, and it's true because they're independent. But let's go through kind of why that's the case. So let's expand this with our Lotus calculation. So we have the expectation. Marker went far. We have the expectation of two random variables. They're independent, but we do have some joint. Basically looking at the expectation of a joint distribution of two independent random variables. So this becomes double sum. So instead of just the sum of over one random variable, we sum from z equals 0 and y equals 0, and actually don't know why these. I guess we're using discrete starting at 0. So from 0 to infinity for z, from 0 to infinity for y, and we have s to the y, s to the z, times the joint distribution of these two. So f of z, y, right? And this is, I'm just using f of z, y as the shorthand for the joint PMF of z and y. I could write this as p of y equals y, z equals z, right? That's the shorthand. I'm just very shorthand doing it. And what's cool is that we know, right? We know that because these two things, z and y, are independent, we know that f of z, f of y equals f of z marginally times f of y marginally, right? They're independent, so the product of the marginal PMFs is equal to the joint PMF, right? So we can just rewrite this guy as f of y, f of z, and now we can rearrange, right? We can take out our z term and take it out from this sum because we're summing with respect to y. We can take out the z, the f of z, and take out the s to the z, and we get this. So z equals 0, s to the z, f of z. We're left with y equals 0, s to the y, f of y. You still see that? Yes. So this, right, we just move the z out because the first summation is only with respect to y. This looks a heck of a lot like this, right? Here's it's crisscross, but here's the expected value of y, right? We're summing over all y, the function s to the power of y, times the PMF of y. Again, I'm using f of y as the PMF. I could be writing probability that y equals y, but these actually should be calculus. Just realized. Okay, here I could be writing p that y equals y. I'm just writing f of y just to be safe space on my finite board. So this is the s to the power of y times the PMF of y. This is s to the power of z times the PMF of z. That's the expected value of s to the y. This is the expected value of s to the z. So basically, checks out, because these two are independent, we can kind of filter them out. And what's really cool is we found that expected value of s to the w is just the product of the expected value of s to the y, the expected value of s to the z. The PGF of w is just the product of the PGFs of the random variables that sum to it, okay? And we did this just for two terms, summing to w, but you can tell that this expands to any sum of independent terms, any number of sum of independent terms. And since a binomial is a sum of n independent Bernoullis, we can just take this PGF, which we found earlier, and just raise it to the power of n. So we're going to get our PGF. We can get our PGF. X equals 1 minus p plus ps to the power of n. So instead of doing the whole summation lotus thing, we just used a little trick that we took the Bernoulli, proved this case that the PGF of the sum of random variables is the product of the individual PGFs, and then we can just write down our new PGF. We can do the quick test, right? We plug in 0 for s, so 0 for s, this ps goes away, we get 1 minus p to the n. That indeed is the probability of x equals 0 or 0 successes. We have n failures, and the probability of failure is 1 minus p. And if we plug in 1, we're going to get 1 minus p plus p to the n, 1 minus p plus p to the power of n. 1 minus p plus p is 1, equals 1 to the power of n. 1 to the power of anything is going to be 1. So checks out. So we showed that our two properties check out, which means it doesn't mean that it's a valid PDF, but it is a good sign that we didn't do something wrong. And again, we found using Lotus, we found the PGF of Bernoulli, and then using a cool trick about PGFs, you probably remember something similar with MGFs, moment generating functions. We showed that we can just take the PGF of a Bernoulli and calculate the PGF of a binomial. So hopefully you enjoyed this video. In the next video, we're going to talk about actually using these PGFs, probability generating functions, now that we have sort of more intuition around them, actually using them to find out some cool stuff about branching processes. So we'll see you then.